Hope from the last class you have full idea how a computer program can form the total structural stiffness matrix of the entire structure from the individual member stiffness matrices. Now let's go to next step, the programming part. Before we go to the full-fledged programming steps, let's see the summary of the entire procedure in class. So the first step is that we have to number all the joints of the structure sequentially, starting from the unrestrained joints. The restrained joints, they have to be numbered in the end. Right now we are assuming that the restrained joints are fully restrained. Later on we will make provision for partial restraining such as hinges or rollers, and we'll also make provision for internal hinges. Next, because now we know all the numbers of the joints, so we can create the total structural stiffness matrix because we know its size. So we just create the matrix and initialize all the elements to 0. Then we have to form a recursive loop involving all the members. One by one we consider each member, we compute its member stiffness matrix in global coordinates. How do we do that? We first form the stiffness matrix in the local coordinates, we form the transformation matrix, and by the procedure T transpose multiplied by KL into T, we obtain the stiffness matrix of the member in global coordinates. Then we form association matrix, and using the association matrix we establish connection between the member degrees of freedom and the corresponding structural degrees of freedom. So once this is established, we send each element of the member stiffness matrix, which is now in the global coordinate system, into the appropriate locations of the total structural stiffness matrix. So we have to do this process one by one for all the 36 elements of the stiffness matrix of the member. So this process, if we do it for all the members beginning from the first member, and each time we keep on adding the elements to the already stored value, then once we complete all the members, we'll obtain the total stiffness matrix of the structure. That is the summarized procedure. We'll learn the detailed steps to aid in programming process from the next slide. So now we write various steps involved in a detailed manner such that we can implement these steps to write a program. The first step is that we label all joints from 1 to n, beginning with the unrestrained joints and then the restrained ones. So we know that if a particular joint is carrying a number I, then the degrees of freedom associated with the joint are 3i, 3i minus 1 and 3i minus 2. So this process in a way numbers all the degrees of freedom also. However, it's the responsibility of the user to provide the coordinate information to the program, because the coordinate information is something which is used for defining the members and also for defining the transformation matrix related to the two coordinate systems, local and global. Next, we label all the elements. Say the number of elements could be m. Here user has to provide the information as to the end joint numbers. User has to provide the near joint number and the far joint number, because these two joints, which is the near joint and which is the far joint, will define the coordinate system. If the two are chosen differently, we'll have different coordinate system. If the near and the far joints, they are chosen the other way, the coordinate system will also be different. This will be further clarified in the last slide of today's class, where a question from a previous year's student is addressed. Then once we have this information, we compute the size of the total structure stiffness matrix, create a matrix with all 0 elements. This is called as the process of initialization. That is, we create a variable and we initialize all the elements to 0. Now we can set up a recursive loop covering all elements. So we repeat for each element starting from member number 1 to member number m. First, we compute its stiffness matrix with respect to the local coordinate system. Then we obtain the joint transformation matrix and then the member transformation matrix, that is R and T respectively, from the end coordinates of the member. Then once we have this information, we obtain the stiffness matrix of the member in global coordinates. Then from the joint information, we establish the association matrix of the member, and once the association matrix is there, we can relate each member degree of freedom to the structural degree of freedom, and thus we can transfer all the 36 elements to the appropriate locations of the total structural stiffness matrix. So this is something like we are superimposing the individual stiffness matrices of the members. So this is represented by this kind of sum. Now it's very important to note that we have to check each of the 36 elements of the stiffness matrix of the member. We may choose taking advantage of the symmetry of the KTS to generate either the lower triangular half or the upper triangular half, because the matrix is symmetric. But from the point of view of the member stiffness matrix, we have to check each of the 36 elements. Now the next step is to form the load vector. Now this would be contributed by either the direct nodal loads, which could be forces or the moments, and this would also be contributed by the member loads. Now the problem here is that in the stiffness method, we deal with discrete quantities like the nodal loads, which are along a particular degree of freedom. So we cannot directly accommodate the member loads, which are sort of spread out. So the process is that we have to convert the member loads into equivalent joint loads, which are sort of discrete and directed along a particular degree of freedom. We have been familiar with this approach. We do this in the case of the slope deflection method and the moment distribution method also, where we find out the fixed ended moments. So same process we have to repeat here. To do that, what we do, we consider two systems A and B. First of all, we lock all degrees of freedom of the structure, and then what we get all the fixed ended forces. This is structure A. Now we have disturbed the structure has been changed. So to restore the structure back, we apply equal and opposite of these fixed ended forces on the structure. So this forms now structure B. Basically, we analyze structure B. Structure B has all the forces in discrete form along particular degrees of freedom. So this can be analyzed easily. So when we obtain the fixed ended forces, we have to convert them into equivalent joint loads. This can be programmed in a very simple way using the transformation matrix. Usually we are getting the fixed ended forces in the local coordinate system. So if we pre-multiply it by T transpose and use the minus sign to bring about the opposite direction, then we obtain equivalent joint loads in the global coordinate system. In this example structure, we have deliberately restrained only the top beam because top beam only has the member load. So we get the fixed ended forces in the form of reactions vertically upward, WL by 2, WL by 2, and the moments at the fixed ends, WL square by 12 in the two opposite directions. Left side we have anti-clockwise, right side we have clockwise. Now equal and opposite of these forces we apply on the structure, and this is our system B as shown here. Now we have to identify that these forces are to be applied along which degrees of freedom. So what we do numbering of the joints and the corresponding degrees of freedom. So we have numbered here the degrees of freedom beginning with 1, 2, 3, 4, 5, 6, which are the unrestrained joints, and then we come to the restrained joints. So 7, 8, 9, 10, 11, 12. So here the degrees of freedom associated with the restrained joints are shown with black color. So our force vector will be 12 by 1, and we can do its partitioning because now we have the information that degrees of freedom 1 to 6 are associated with external forces, 7 to 12 are associated with reactions which are unknown. So essentially we'll analyze structure B using the direct stiffness approach, and after we get the results we'll superimpose the results of structure A, because structure A, the results are standard, they are to be added to the member end forces only. There are no displacements involved in system A. So you try to fill up the different elements of the force vector using this information. Like along the degree of freedom 1 we have the force P1, which is the direct joint load. Then along the degree of freedom 2, what value will be filled up? It will be minus WL by 2. Along the degree of freedom 3, the moment will be acting, and this is basically clockwise moment, so we fill up here minus WL square by 12. Along degree of freedom number 4, 0 will come. Along 5 it will be minus WL by 2, and along 6 it will be plus WL square by 12, because now we have anti-clockwise moment. So now we have the force vector P, and from 7th row onwards we have the unknown reactions x7, x8, x9, x10, x11 and x12. So we have our force vector where we have the prescribed forces and the symbolic unknown reactions. So by now we have all information to set up our system of equations. The load vector has already been partitioned, and by the same number of rows we can partition our stiffness matrix also into KPP, KPX, KXP and KXX. From the point of view of the columns, the same size KPP is a square matrix, so we can partition along the columns also in the same manner. So we have on the right hand side the unknown displacements UP and UX, the known are the prescribed displacements. They could be either 0 or they could have a fixed value in the case of support settlements. So let's first consider the case that there is no support settlement, so the prescribed displacements, they are all 0. Then we can begin with the first equation from the top, P equal to KPP UP plus KPX UX. So UX is 0, so the equation gets simplified into P equal to KPP UP. Then the solution is very simple. All we have to do is find out the inverse of KPP and pre-multiply it with P, and we get the displacements. The unknown displacements are with us. Then we come to the second equation, that is x equal to KXP into UP plus KXX UX, because UX is 0, so simply we get the reactions as KXP into UP. So that way we get both the displacements and the reactions. However, if the support settlements, they are not 0 and we have the fixed known value, in that case the only difference is that we have little bit additional computation. Instead of the usual load vector, we can say that we have a modified load vector P star, which includes contribution from the support settlements also. Rest of the steps are same. Once we have the unknown displacements UP, then we can make use of the second equation and obtain the final reactions. So this process helps us in computing the unknown displacements and the reactions. Next question is that what additional information do we need to find out? We say that we are analyzing the structure. So far we have obtained the displacements of the structure. We have also obtained the reactions. What else do we need to complete our analysis? The answer is that we need to obtain the member forces, because member forces are what based on which we can design the structural members. So we'll cover in the next slide how to obtain the member forces. Now this is the last step. We have to get the member and forces. Usually we need member and forces in the local coordinate system because then it's convenient to design and also to visualize. Now how do we get that? The first step is that we have to do for all the members following. That first, using the association matrix, we have to find out what are the displacements at the two ends of the member. For example, let us look at this member marked star. Let's say the user has named joint number 5 as the near end and joint number 2 as the far end. Then we can get how the member degrees of freedom, they are related to the structure degrees of freedom. So the association matrix of this particular member would be 13, 14, 15 because these are the degrees of freedom associated with joint number 5, and 4, 5, 6 because these are associated with joint number 2. Hence we can then extract the displacements pertinent to this member as shown below. That is, D1 is U13, D2 is U14, D3 is U15. Similarly, D4 is U4, D5 is U5 and D6 is U6. So what are U13, U14, U15, U4, U5, U6? These are the joint displacements obtained from the analysis in the previous step concerned with the structure as a whole. So the displacements connected to each member are basically a subset of these overall structural joint displacements. So these displacements D1, D2, D3 till D6, they are uppercase. That means they are with respect to the global coordinate system. So first of all, we convert these into local coordinate system by pre-multiplying with the transformation matrix T. Once we have the displacements in the local coordinate system, we can make use of the stiffness matrix of the member in local coordinates to get the member and forces. But this is not the end. We also need to do correction for the fixed-ended forces, because if this particular member has some member load and we had restrained this member to obtain the fixed-ended forces, then part A has to be added. The result till step number C is for part B. So result of part A has to be added, and when we add the fixed-ended forces to the member end forces obtained from the previous step, then we get the final answer. So hence till this step we have obtained all the member end forces also.
So the sequencing is not getting clear. Whatever the action, the 13, 14, 15 or 4, 5, 6. When you are achieving the member 2 and 5, it should be only 4, 5, 6 and 13, 14, 15. Then how the sequencing is being done?
Sequencing, it depends on how you are defining this member, local coordinate system. If you are defining or your local coordinate system that this member 2 and 5, let's say, is like this. That this is the first joint, this is the second joint. So this is our local x-axis. This is our local y-axis. Then your degrees of freedom numbering will be like this: 30, 40, 15 and 4, 5, 6. But if you have defined it the other way, in the other way means that you are defining your local x-axis down. Now where will be your y-axis? Because the z-axis, local z-axis has to go out. So right-handed rule, now where should be your local y-axis?
It's towards
Towards? Left.
towards right.
Left or right? It has to be towards right. It has to be towards right, then only we have the right-handed system that your Z will point towards you. So if you are adopting this, then your first joint is true and your second joint is fine. And both ways, your matrix will be different, but you have to be consistent. If you interchange in between, your results will be wrong. So don't have to interchange in between. So you have to be consistent. Okay. Any question? So if this is understood, then half of the problem solved.